Thanks a lot, Matt. And I want to start by saying that this has been a really wonderful conference, I think, for all of us, the people, the mathematics, the location, everything. So I really want us to thank the organizers, Andres, Selvi, Matt, and Dan. All right. So what I plan to tell you today about is this class of combinatorial objects that I've been thinking about now for a while, for a decade or something, called tropical ideals. And for this talk, I want to just focus on the very combinatorial structure of these things. So I'm not going to do any. I'm going to try to distill the very combinatorial essence of what I'm trying to say. So let me. I'm also not going to assume that you know anything about tropical geometry. So I have one slide like telling you my view, or what I want us to have as the view for what tropical geometry is. In a nutshell, tropical geometry is some tool that allows you to take some algebraic variety, like this one that I have over here, some cubic curve in the plane. You tropicalize it doing some operation that we'll talk about in a second, and you get some polyhedral object, some combinatorial polyhedral object out of it. And the idea is that this preserves some information that you're maybe interested in about this algebraic variety, right? Like the dimension, for instance, is preserved by this process, or the degree, or you can recover many things. And this has been successful, like algebraic geometers or tropical geometers like this approach, because some problems you cannot try to attack now in the combinatorial, in the tropical side. And for some questions that are well posed, you can try to solve the problem here, and you get the same answer that you would get in the classical world. So for instance, it was very successful. This was very successful, and this kind of got very popular when people realized that you could compute something called Severi degrees, which amount to like counting how many cubic curves that in the plane that go through 8 generic points, how many curves there are that go through 8 generic points and have one self-intersection, one nodal singularity. And if you do the count tropically with the right multiplicities, you get 12. And it turns out that you can prove that 12 is the same as the number of classical curves satisfying that. Okay? So just some machinery that allows you to turn algebraic geometry into kind of combinatorial problems. All right. But let me talk a bit more about what this process is that turns an algebraic variety into a tropical variety. So let's say you have a variety V, an affine variety V as a variety of affine space in n-dimensional space, which is the zero locus of an ideal J. So J is an ideal of polynomials that describes what your variety is. And then when you have a polynomial F that I'm going to denote by this with this multi-index notation, so one monomial for every lattice point, and the coefficient of that monomial is CU. I'm going to denote the support of the polynomial to be the collection of lattice points, the collection of monomials where the coefficient is not 0. So that's the support of one single polynomial. Now the tropicalization of the ideal, think of it as the collection, the support of all the ideal, not just of one polynomial, but of all the ideal, is just the collection of all the supports that you see for all the polynomials in your ideal. Okay? So this is a finite subset of lattice points, and this is a collection of finite subsets of lattice points, right? And everyone has been playing with these boards and uncovering amazing stuff. I had to do something about that. But I'm going to be using this the whole talk, so I really want these to stay here. Support of a polynomial is just the monomials that appear, the lattice points, and tropicalization of an ideal is, think of it as the support of the ideal, is the collection of all supports that you see. All right. Okay, so what is the tropicalization? I told you how to construct this like combinatorial essence of the ideal. The tropicalization, so the tropical variety, the polyhedral complex, is you look at all the directions in R to the n, all the directions A, for which for all the subsets in your tropicalization of the ideal, the direction is pointing to at least 2 terms of 2 lattice points. Okay, so when you look at the face maximizing, the face of S maximizing the direction A, there's at least 2 vertices that are maximizing that direction. So another way of saying this, and we'll have an example in just a second, just to make sure that we're all together. So the directions that point to at least 2 vertices in a subset S is just the codimension 1 skeleton of the normal fan of the convex hull, of the Newton polytope, of the convex hull. And then you intersect, of the normal fan of the convex hull, and then you intersect all those for all the subsets in your tropical ideal in this direction. All right, I'm going to have an example just like John said, please don't get bored. Please ask me questions just to make sure that we all understand. So let's tropicalize a line, a very simple ideal, a very simple aligning in two-dimensional space. Let's say that our line is the zero locus of x plus y plus 1. So x plus y plus 1 equals 0. That's the line we want to tropicalize. Let's consider this ideal with coefficients in some field, our favorite field, maybe the complex numbers. So as an ideal, J consists of the generator, but also like x times the generator, y times the generator. Some interesting things can happen. For instance, if you take this one minus that one, so x minus y times the generator, you get this polynomial. And of course, there's infinitely many polynomials in your ideal. Then you tropicalize that ideal, meaning you just collect the supports that you see for all the polynomials. So the first one, and I'm not going to write the lattice points, but I'm going to identify monomials with lattice points because I don't want to start writing long sequences of lattice points here. But this is like 1, 0, 0, 1, and 0, 0. That's one collection of, that's the support of this polynomial. The second one has this support. This third one has this support. So just collect the monomials that appear in every polynomial and put them in a set. And then look at all directions that for each of these, they point in at least two of, like they select at least two of the monomials appearing. So for instance, these three form the convex hull of them is like a triangle like this. And then the directions that point to two of those are either completely horizontal to the left or completely vertical down or slope 1 in this direction, which is when you pick two of the three vertices. And if you think about it, because all these polynomials were multiples of that one, actually all these polytopes, like the convex hull, are going to have this one as a summand. So these do not impose any new restrictions. Like if you pick two elements here, then you're also going to pick two elements in this. So this is really the tropical line, the collection of directions that for each of these pick two elements. Good? Are we? Yes?
Is this the are the outer normal or the inner normal?
Outer normal, yes. I'm going to use the max convention for this talk so that this is directly dual to the Newton polygon here. Good. And it's not obvious from the way I defined it here, but one of the main things that and why people like this tropicalization process is that actually, even though you have like infinitely many conditions here, because there's infinitely many polynomials, what you get is a finite polyhedral fan. So you really get only like finitely many faces. So you can study combinatorially. It preserves, this is quite amazing, that it preserves things like dimension, for instance, because where it started with a one-dimensional variety, a line in P2, in A2, then the tropicalization is a one-dimensional polyhedral complex. And even there's more structure that these fans have. So for instance, you cannot, it has to be like a balanced polyhedral fan. What that means is that the maximal cones come with some like weight, and when you think of like people pulling with that weight along these directions, then this middle point wouldn't move, right? So for instance, all these rays cannot be pointing all to the left because that wouldn't be balanced. They need to be like spread out and have a zero tension condition around every codimension one phase. Yeah. So there's a lot of structure that these things satisfy, and it's kind of miraculous that such a simple construction results in such a structured object. Good. So how did tropical ideals start? I'm going to tell you a bit of the story of why we started thinking about this. Well, in 2013, Jeff and Noah Giansiracusa, two brothers, they wrote this paper where they say, okay, we've been thinking about tropical geometry as understanding these tropical varieties, these polyhedral complexes, but in algebraic geometry, we don't do that anymore these days. We think about schemes, we think about like algebraic varieties or algebraic schemes as like given by some algebraic information that you glue together. So maybe we should try to think about algebraic information for tropical geometry as well, like try to define tropical schemes. And they gave a definition for what an affine tropical scheme is. It was in terms of some congruence of polynomials in the tropical semi-ring. And maybe I don't want to say too much about that, but later with Diane McLagan in this paper in 2014, we realized actually what they were proposing that was a bit more complicated. It's just equivalent to this collection of subsets of supports that appear in your radial, okay? So really, an affine scheme, you should think like the algebraic information corresponding to an affine variety in tropical geometry is this collection of supports of polynomials, something like that, okay? At least if you start with a polynomial with coefficients in a field, with a classical ideal. And then in another paper, we later said, okay, we noticed the following, well, of course, these collections of supports of polynomials have some structure themselves, right? Not every random collection of subsets of lattice points is going to appear as the collection of supports of polynomials in an ideal. So actually, I like doing some audience participation in my talk. So I want us to discover like some combinatorial properties that these collections of supports satisfy. I'm going to start with I'm going to cheat. I'm going to start with the simplest one, which is that actually I claim the empty set is in any of those collections because the ideal has the zero polynomial and the support of the zero polynomial is empty. Okay, so all the collections that appear like this have the empty set as one of their subsets. Can you guys tell me some other combinatorial properties that these collections of subsets have to satisfy? So the ones, what I mean is like collections that arise like this, right? You start with one ideal, and you look at all their supports. There's some structure that these supports satisfy. Can you guys maybe tell me? Yeah?
Is it like if you, like I'm thinking matroids, so like if you have the thing, you have some element that's in your set and then something that's contained in that element and that thing that's contained in it also has to be in there?
Yes, that is right. That's not the first one I have in my slides. We're going to have to wait three slides for that one. Yeah. But like simpler ones, yeah.
I was going to say, so this x, y, 1, if you multiply that by x, you can multiply it by y, or you could like
excellent. Thank you, Galen. This is the first one I had over here. If one support appears in your collection, then, well, that support shifted by a variable, like if you add E1 or EI to all the lattice points that appear there, that should also appear because this is the support of taking the polynomial here and multiplying by x or by y or by, okay? So it's invariant under, or not invariant, it's closed under shifting in coordinate directions. Can you guys think of other properties that these collections of supports should satisfy? What if we take two polynomials in the ideal and take like a linear combination of them? What can happen? What's the support of that linear combination? The union, right? I guess I'm assuming that the field is infinite, so you can take like really a generic combination of the two. Like you take this polynomial and that polynomial and take some generic combination of them so that nothing cancels out, no monomial cancels out. Then you see that, well, if two subsets appear in your collection, then the union of the subsets appear in your collection. And this is for infinite fields, but yeah. And then the third one, maybe, Anastasia, is what was related to you say, is some kind of matroidal condition, which is that actually you take two polynomials and you don't take a generic combination anymore, a generic linear combination, but a special linear combination trying to eliminate something that they have in common, then you get the following. So suppose you have two subsets in your collection, and they share some common lattice points, some common monomial. Then you can think that these correspond to two polynomials, and you can like take the DS pair corresponding to those two polynomials that eliminates that monomial. And in that way, you will get a third polynomial that only uses monomials that appear in the union. It doesn't use the one that you eliminated. But if a monomial appeared in only one of the two, then that one cannot cancel out. And so you get, it should be included in this three. Yeah? Does that make sense? And then, yeah, so we noticed this in this paper. And then what the paper was about is we proposed, okay, why don't we study these collections, like the collections of subsets that satisfy these combinatorial conditions as combinatorial objects on their own. Let's forget that these arise as coming from some ideal with coefficients in a field, that they are the supports. Let's just try to understand what can we say about collections of lattice points, collections of subsets of lattice points satisfying these combinatorial conditions. So this is, of course, yeah, there's a much more general version of what I'm saying for toric varieties with coefficients that are not trivial valuation. But as I said, I just want to tell you guys what like, the baby case, which is already super interesting, and there's lots of open questions that I want to talk to you about. So the definition we propose is that just a collection of subsets of lattice points is going to be called a tropical ideal if it satisfies these four conditions. And of course, the main example we should have in mind is that whenever you have an ideal with coefficients in a field, like an honest ideal, like the ones we usually work with, when you take the collection of supports, you get something like this, and we want to think of those as the realizable ones. So this is like the combinatorial objects. Some of them are realizable by an ideal, but some of them might not. And it turns out that there are lots of non-realizable examples. let me make one comment on the definition. So I'm just going to copy this definition over here as well. This is just a tropical ideal is something satisfying those four axioms. And then, because we all like matrix here, or yeah, I believe that's the case. Most talks have mentioned the word matrix, I believe. So the way I presented this definition is a bit ad hoc, but it really is very natural. So I'm presenting it like this so that it's kind of natural, but I also want to tell you that it's very natural from a point of view. And if you think about it, what we're saying is, let's denote by delta D the set of monomials of degree at most D. So like truncate your infinite lattice by some degree, and consider the truncation of your collection to only subsets that involve monomials of degree at most D. Then, well, it turns out that Ti0, Ti2, and Ti3 are exactly saying that that collection of subsets is a matroid on that ground set. So this should feel something like a circuit elimination axiom, and it's actually not the circuit elimination axiom, but it's the elimination axiom for unions of circuits, which are like cycles. If you go to one of these matroid books and you look, what's the cryptomorphism for matrix for unions of circuits, you'll see exactly these three axioms. The empty set is a union of circuits. If you take two unions of circuits, then the union is a union of circuits. And unions of circuits satisfy this elimination axiom because circuits you can eliminate. So 0, 1, and 3 are exactly saying that when you take a restriction, you get a matroid. But then these matroids are like compatible in some sense, right? So you have one matroid for every degree, but they need to like fit together in the sense that if you take something of degree D and you multiply it by a variable, you should get something of degree D plus 1. And then here's an equivalent definition based on basically what I just said, which is actually the way I think about tropical ideals. It's an infinite tower of compatible matrices. So the ground sets of these matrices are monomials of degree D. You have a matrix on the variables, matrix on the quadratic monomials, matrix on the cubic monomials, and so on. They need to like extend the previous one, so they're like sitting top of each other. The matrix of monomials of degree 2, when you're restricted to monomials of degree 1, is the previous one, and so on. So it's like an infinite tower of matrices that keep extending and extending the other. But they need to satisfy this condition that if you take a circuit, a union of circuits of degree D, and you multiply it by a variable, you get a union of circuits in degree D plus 1. And there's a matroid name for what that is, and I wrote it here. It's called the matroid quotient, if you have heard about that. So it's saying that for every variable, when you take your matroid in degree D and you multiply it by a variable, then you get a matroid in degree D plus 1, and that should be the restriction, or a quotient of the restriction of the one that you have in D plus 1. Restricted to those monomials, the monomials that are divisible by x. Okay, yes?
Is it the same thing as like an extension or a lifting, or is it kind of different?
No, it's a different. It's kind of the opposite of a lifting. So a lifting, so here you don't extend the ground set, but they have the same ground set. It's just that a quotient, another way of defining quotient is you make a lifting, but then you contract what you extended. And that's a quotient. And actually, yeah, if you're not familiar with this word quotient, you can just say isomorphism, and that gives you a slightly restricted class of ideals in which the matrix that you have in degree D is exactly the same matrix that you see in degree D plus 1 restricted to those monomials. You guys are commutative algebraists, a lot of you, so think of that as just the ideals that are saturated with respect to the product of the variables. But if you already see a polynomial that appears in degree 7, but it's multiple of some variable, then you saw it in degree 6 before. And that's still super interesting. So it defines schemes of the torus instead of affine space, and we're also lots of questions about those. So yeah, just think you can say here that this is an equality. Good. Does that make sense? Maybe this is kind of the main. It's hard to extract this if you read the paper because it's done on more generality, but the main thing I want to tell you guys is that tropical ideals are just very natural objects that are very simple, and think of it as a tower of matrix that tells you what polynomials are in it.
So is there such a thing as saturating tropical ideal?
That's right, saturating by a monomial, yes. So you can, if you take a tropical ideal, it's a collection of subsets, and you saturate by a monomial, that's kind of a combinatorial operation, and that's why you can do it at the level of supports, and it preserves being a tropical ideal, the saturation. So yeah, whenever you have one of these, you can saturate and get one where you have these.
Does that preserve some geometric information, like in the case of commutative algebra?
Absolutely, yeah. So the variety, I haven't talked about varieties, but the variety is going to be the same, but you remove the components at infinity. The components outside of the torus. let me give you examples of these. So for instance, let's do another audience participation, I'm not sure. How about we take one variable, so supports, imagine you're thinking, yeah, polynomials in one variable, and let's take I to be the collection of subsets that have at least two elements. So like, now the ground set, like the polynomial, the monomials are 1, x squared, x cubed, and the collection of supports is everything that has at least two sets. 1 and x squared, x and x cubed. That's a tropical ideal, but let me ask you guys, is this realizable or not? Can you think of a classical ideal with coefficients in a field where the supports that you see are exactly all subsets of monomials that have at least two, like 1 and x squared, x and x cubed, x and x squared? Does that make sense? So it should be an ideal in one variable, right? So my ideal here. And I want the polynomials here to have supports any pair of monomials that you give me, or more, or triples of monomials, or quadruples. Well, if you think about it, you need to have like 1 and x need to be the support of some polynomial here. So for example, you need to have something like x minus 1, a polynomial here. And once you have x minus 1, you have like x squared minus 1, because x squared minus 1 is a multiple of x plus 1. So if you think about it like this binomial ideal, what are the polynomials that appear in there? Well, it's exactly all binomials, like x minus 1, x squared minus 1, and also x cubed minus x if you multiply that one by x, and so on. And by adding these binomials, you can make any support that you want, but you'll never make a singleton. Those are the ones that are excluded. But anything that has at least two terms appears as polynomials. So this is a realizable ideal, tropical ideal. And for a while, we didn't know of an example of a non-realizable ideal because constructing these things is quite difficult. They're quite tricky. But then I learned about these matroids that I like a lot from a paper of Federico Ardila and Sarah Billy on flag arrangements of subspaces. And it turns out that they provide an example of a non-realizable ideal. So let me tell you what this is. So this is an ideal in two variables. I'm going to be talking about monomials of two variables, x and y. And the subsets that I'm going to include in this ideal are, well, the minimal subsets that I'm going to include in this ideal are subsets that consist of k plus 2 monomials inside a triangle of size k. Okay, and a standard triangle of size k. So standard triangle, I really mean like a triangle that is like vertical, horizontal, and slope minus 1. So for instance, whenever you see 3 monomials inside a triangle of size 1, that's going to classify as something in your ideal. Like 1, x, and y are 3 monomials inside this little triangle. So this is one element of your tropical ideal. Here you also have like those same but multiplied by y, xy, and y squared. There are 3 monomials inside a triangle of size 1, so that classifies. Here I have an example of 4 monomials inside a triangle of size 2. So k plus 2 inside a size k, that classifies. Here are 5 inside a triangle of size 3, and so on. Okay? It turns out, it's not obvious from this description, that these are like I'm telling you, the matrix of degree 1 is this one, the matrix of degree 2 has things like this, the matrix of degree 3 has things like this, and it's not obvious that this is a matrix, that these subsets satisfy the circuit elimination axiom that I told you about, but they are, and this is what I discovered in the paper I mentioned. So I'm telling you a collection of matrices for each degree. They are compatible, they sit on top of each other. So like you see, this one restricted to these 3 monomials is exactly this one. And it's also invariant under translation. If you see these 3 monomials inside a triangle of size 1, when you multiply them by y, you're still going to get a subset here in degree 2. So they provide a tropical ideal. But I claim that this is not realizable. You're not going to be able to find an ideal with coefficients in a field where these are exactly the supports of the polynomial. And the proof is not that difficult. The proof is a one-line thing. Suppose it was realizable. Suppose these are exactly the supports of the polynomials in some ideal I or j with coefficients in a field k. Well, because you have this subset, 1x, y, that means that some linear polynomial has to live in your classical ideal. You can scale the polynomial so that this coefficient is 1. You can scale the variables so that these coefficients are 1 as well. So without loss of generality, you can think that x plus y plus 1 lives in your ideal. But then any multiple of x plus y plus 1 is going to live in your ideal. So take that polynomial and multiply it by this like carefully selected polynomial that creates a lot of cancellation when you expand this out. And what you get, only 4 terms survive. X cubed, y cubed, 3xy, and that one, depending on the characteristic of the field, might have survived or not, and 1. And in any case, these are like 4 monomials that don't live in a triangle of size 2. They're like spread out. So this is not one of the subsets that you included in your ideal. So this is a contradiction, because then this would force these 4 monomials to appear in your tropical ideal, but we didn't put them there. So it's kind of an interesting, I like this example a lot for many reasons. But one thing that I find interesting is that even though all these matroids are realizable, so these are transversal or co-transversal matroids, I forget exactly. These are realizable matroids. The one you put in degree 1 is a realizable matroid. This one is a realizable matroid. All of them are realizable, but kind of when you stack them one on top of each other and think of them as an ideal, you cannot realize them by a single ideal. Yeah. So realizability is tricky, is what I'm saying. It's realizability of ideals. And constructing these non-realizable ideals is hard. And I would love to know more examples. This is basically one of the few examples we know of non-realizable ideals. Questions so far? Does this make sense? Good. This is actually the first time I think I talk to a community where there's a lot of commutative algebraists, and that's very exciting. So I'm going to try to emphasize the commutative algebra behind all this. So let me tell you, I mean, in my opinion, the definition is very natural, and especially if you come from tropical geometry, the definition, you can say something equivalent to like a tropical ideal is an ideal in the semi-ring of polynomials where every truncation is a linear space, a tropical linear space, because matroids are like tropical linear spaces. So the definition is very natural, but the question is, okay, what can you say about these things? Are they really, are they useful for coming up with algebraic foundations of tropical geometry? And there are some positive results in that direction. So for instance, if you think about it, they already come equipped with a notion of a Hilbert function, because you have matroids, and matroids have ranks, and yeah, that gives you a Hilbert function. So the Hilbert function of a tropical ideal is the function that records for every degree the rank of the matroid that you're putting on that degree. The rank of the matroid that tells you what the monomials of what the polynomials of degree at most d are. If you don't remember how to get the rank from the circuits, well, another way of saying this is the size of any maximal subset of monomials that doesn't include already one of the supports that you had. Okay. So just to practice this, let's think about what the Hilbert function of these tropical ideal would be. So for instance, in degree 1, it would tell you how many monomials you can pick without selecting these 3. So that's 2, right? In degree 1, this has dimension, this has rank 2. Here in degree 2, it would tell you how many of these 6 monomials can you pick without including one of the subsets that you put in there. Can you guys see how many monomials you can pick without including subsets like this one or like this one? What's the maximum size? 5? Which 5 can you? I think it's less than 5. Like whenever you pick 5, you're going to pick either a triangle like this, or this one, or this one. And also 4 is not going to work because you include things like this. So I think it's 3, actually. 3. If you pick, for instance, these bottom 3 monomials, those do not include any of these. But as soon as you put one of these, even that one there, these are 4 monomials inside a triangle of size 2. So anyway, so the Hilbert function of this is actually d plus 1, 2, 3, 4, so degree plus 1. And you should expect that because actually it should be a line. It's a scheme that gives you a line. So the Hilbert function should be the Hilbert function of a line. But okay, the point is that these things have a Hilbert function, and it's a generalization of the Hilbert function of an ideal. See, if you take an ideal, a usual ideal, the ones we work with, and you tropicalize it, then these two notions are the same. The Hilbert function defined in this combinatorial way is just the same as the Hilbert function of the ideal as computed as the dimension of the quotient ring. Yes, sorry. I was thinking homogeneous here, but I changed to affine over there. Yes?
So does this somehow mean that if you have one of these ideals at some point, if you know the first, like, let's say, K matrix, you can determine the rest?
I would love that. That's literally what you said is not true, but I would love something like that. This is saying that there's the way the rank grows in these towers of matrices is very controlled. You cannot just make it grow arbitrarily because it needs to become polynomial at some point. And I don't know how to, this must mean something like that, but I don't know exactly. So the theorem that you can prove is, I said it, but is that the Hilbert function defined in that way is eventually a polynomial, okay? No matter if the ideal is realizable or not, we know that this is something that happens for realizable ideals, but even if you take one of the ones like non-realizable ones, the growth is gonna be polynomial, yes?
So then does that mean that you have like a notion of regularity because you know, like, can you say like, oh, at this point is when it becomes polynomial? Does that mean something or no? Or you don't?
Yeah, again, it's a similar question. Like I would love to say something like, yeah, you understand the ideal from there on, and then something weird can happen below those degrees, but that's not completely clear. This is, Also, one of the things I tried to do for the presentation is to give you guys lots of open questions that maybe you guys can help me with, because, Something else that is quite interesting for tropical ideals, and this does require some, is that, well, these tropical ideals are typically not finally generated. As it's not true that if you just pick some fixed collection of subsets and like take all unions of them and multiples of them, you'll get a tropical ideal. So you really need like infinitely many generators, but still they satisfy the ascending chain condition. So we're kind of in an Ethereum situation here where you cannot find an infinite ascending chain of tropical ideals in a fixed number of variables. Yeah?
Is the proof of the theorem in the middle going through algebra?
I love that question because that's exactly what I'm going to say here. I want to go a bit into the detail of that just for this crowd, which is that we think about Grobner degenerations of tropical ideals, and that works well, and that's the reason why those two facts are true. So how can you do Grobner degenerations for these combinatorial ideals, for these tropical ideals? Well, suppose you have a subset of lattice points, like one of these combinatorial polynomials, and you pick a weight vector, a vector that assigns a weight to every variable. Then you can define the initial term of your collection of lattice points as just pick the lattice points that maximize the weight, the dot product with W in your subset, okay? So if you'd like to think polyhedrally about this, then just think it's the face that is maximized, that W is pointing out in your subset S. So that's the initial term of one single subset. Now, if you have a collection of subsets, like a tropical ideal, you can define the initial ideal by just gathering all the initial terms of all the subsets that you see in your collection for all the subsets that are in your ideal. And the key fact, and this is a fact about matroids that makes everything work, is that tropical ideals are closed under this degeneration operation. So if you start with a tropical ideal, then whenever you take the initial ideal, that's still tropical. It still satisfies this elimination axiom. It still preserves the matroidal property. And in fact, if you start with something homogeneous, then it preserves the Hilbert function. Then you degenerate your matrix to matrix with like fewer bases, but the rank of the matrix are the same. So it preserves the Hilbert function when you do that. So for instance, let me go back to the previous slide and tell you how we prove something like this. To prove that the Hilbert function of any tropical ideal is eventually polynomial, what you can do is you take a generic weight vector, deform your ideal to a monomial ideal by using that degeneration, and for monomial ideals, where monomial ideals monomial tropical ideals are the same as like classical monomial ideals. The addition doesn't play a role in a monomial ideal, right? So the Hilbert function is just counting how many monomials. It's the same Hilbert function as for a classical ideal, and we know that those are eventually polynomial. Yeah, so we can degenerate every tropical ideal to a monomial ideal, and then we know that those Hilbert functions are eventually polynomial. Something similar you can do here. Suppose you have a chain of tropical ideals. Degenerate them to monomial ideals, all of them, by taking a generic weight vector. So do a Grobner degeneration. Now you have an infinite, or a sequence of monomial ideals. Those, by the classical combinatorial facts, we know that those have to stabilize. And then you can go back and argue that, okay, actually the original sequence before you degenerated had to stabilize as well. So Grobner degenerations work well, and that's one of the things that makes a lot of things work in this setup. Yes. Yeah, excellent. Sorry, homogeneous just means that that the subsets that you have in your collection can always be written as unions of things that live in a single degree. So, like your generators, you can make them live in just a single degree. So, for instance, if we go back to this picture, this is really not homogeneous because here you have a generator that involves things of degree 1 and degree 0. But if your generators, like all of them live in these slices of the same degree, then you say that it's, and everything can be constructed as unions of those, then that's homogeneous. Where was I? Here. Okay, so, well, there's Grobner degenerations, and of course, then there's a Grobner complex, which is just take the space of weights, take R to the n, and partition it according to what the initial ideal for that weight is. So fix the tropical ideal and consider all the possible initial ideals you can get. Partition your weight vectors W according to what that initial ideal is. And, well, this is what we call the Grobner complex. It's generalizing the Grobner complex for usual ideals because, yeah, these constructions are all commute, tropicalizing and taking Grobner complex commute. So the Grobner complex of the tropicalization is the same as the Grobner complex before you tropicalized. And one thing we can prove is that, and this again here, it uses really the matroidal property for tropical ideals, that whenever you do the Grobner complex, this partition of the space of weights, for a tropical ideal, you get a finite polyhedral complex, okay? You don't get infinitely many cells, you get only finitely many, and they really glue together on faces. And so, yeah. Yes, does that make sense? Now, what's the variety? We started talking about variety. You can also define like the tropical variety of a tropical ideal. And what we do is we just follow the convention we have in tropical geometry, or we do the natural construction, which is we look at the directions that for every subset in your ideal, the maximum is attained at least twice. So just the same thing we had done before, like this. Yeah. Another way of thinking about it is that you take the space of all weight vectors for which the initial ideal contains no monomial, no singletons. Yeah, and we had talked about that definition already. So every tropical ideal is going to have some variety, some subset, yeah, some variety associated to it. And because this is a subset of a sub-complex of the Grobner complex, right? It just consists of all weight vectors where the initial monomial, the initial ideal satisfies some property. That means that you're just picking some of the cones of the Grobner complex. We had proved that the Grobner complex was a finite polyhedral complex. That means that the variety is going to be a finite polyhedral complex. And this is very much false if we restrict to like more general ideals that don't satisfy the matroidal condition. So here, to have a finite variety, you really need matrix to be underlying your subsets. And in fact, yeah, if you look at the proof, you see that what you're actually saying is that the variety of the ideal is cut out by finitely many subsets, so just like finitely many conditions, like in the first example that we did where we saw that just the generator was enough to cut out the whole variety. In general, you're going to have finitely many subsets that determine the variety, not the ideal, the variety, and we call that a tropical basis. So, all right. Later, we were wondering, okay, this is a finite polyhedral complex, but does it really look like a tropical variety? Does it really have this like balancing condition that if you pull on every cone with some weight, you get a zero tension condition here? And it took us a while, but we managed to, yeah. These really look like tropical varieties in the sense that they're balanced polyhedral complexes. And one thing that is nice is that the dimension of the variety of the polyhedral complex is really the algebraic dimension of the ideal, so the degree of the Hilbert polynomial, which is something that happens classically, of course, but yeah, for these combinatorial ideals, you can also have you also get an equality between the geometric dimension and the algebraic dimension. As a tropical ideal, exactly. Yeah, so even if I is not realizable, this also works for non-realizable I's. It might not come from a classical ideal, but still you have some variety associated to it, and you have some Hilbert polynomial, and that variety has the same dimension as the degree. The leading coefficient is the degree, normalized degree. Degree defined as number of intersection points when you intersect now with a tropical hyperplane. So yeah, some tropical hyperplane, you count the number of intersections with the right multiplicities. That is what the leading coefficient is capturing. Yeah. Any more questions? Something that, for example, I don't know, and maybe you guys have some ideas for this, is we don't know what it would mean to say that one of these combinatorial ideals is prime, is irreducible, right? So we don't know some kind of useful natural combinatorial condition or algebraic condition that ensures that, for instance, when you look at this variety, you get some pure polyhedral complex. This is something that is true for tropicalizations of prime ideals, but yeah, like knowing that the classical ideal is prime is not clear what that implies about the supports of the polynomial. So there is no condition that I know that ensures that behaves as being irreducible. Something else, maybe if you guys like matrix, I started wondering, okay, how general can the polyhedral, the varieties of these tropical ideals be? Okay? We know that they are balanced polyhedral complexes. They're polyhedral complexes and they satisfy the zero tension condition, but can you get any balanced polyhedral complex as the variety of an ideal? Especially because we have non-realizable ideals, then maybe there's enough room to like capture all balanced polyhedral complexes as varieties. And that naturally leads to the notion of a tropically realizable matrid. So I'm going to say that a matrid on the numbers 1 up to n, on the ground set 1 up to n, is tropically realizable if you can construct a tropical ideal on those variables. So monomials, these are the monomials of degree 1, but then you'd have to have a matrid that tells you what the polynomials of degree 2 are, and so on, such that the variety of the ideal that you constructed is the Bergman fan of the matrix. So this is just some polyhedral representation of the matrix that we know is a balanced polyhedral complex. So there's a chance that it can appear as the variety of some ideal. The question is, we're going to call them tropically realizable if it does appear as the variety of an ideal. And kind of by definition, if you untangle all this, you see that if the matrix that you start with is realizable, then it's also tropically realizable because you take a realization of the matrix, take the ideal generated by that linear realization, and the variety of that ideal is the subspace. And when you tropicalize that subspace, you get the Bergman fan of the matrix. Okay. So this is some class of matrix that includes the realizable matrix. And we were wondering, okay, is it all matrix? Maybe that you can always find this. But then with Jan Draaisma, we proved that, or we realized that some old results of matrix theory imply that the Vamos matrix, which is, if you don't remember what that is the matrix like given by that point configuration. Direct sum the uniform matrix 2-3 is not tropically realizable. You cannot construct a tropical ideal on 11 variables. So this is a matrix on 8 variables. On ground set 8, this is ground set 3. So you would have to have 11 variables, and basically, the matrix on degree 1, on the 11 variables, would have to be this matrix, but then you have to construct matrices on monomials of degree 2, monomials of degree 3, that are compatible with what you had in degree 1, and it turns out that's impossible. Maybe I won't say too much about that, but it boils down to some old result of Las Vernias saying that there is no tensor product between these two matrices, and you can ask me later what that is.
So
Yes.
So like U23 is tropically realizable.
That's right. U23 is tropically realizable. So if you take, actually U23 is thanks for that question, here is a tropical ideal that realizes U23. This is the Bergman fan of U23. And here is a tropical ideal whose variety is the Bergman fan of U23. And the reason this is true because U23, I'm taking a realization of U23, just one linear form on 3 elements. And if this is the tropicalization of that, then the tropical variety is the tropicalization of this. So realizable matrices are all tropically realizable. But yeah, you're saying U23 is realizable. What about this? Is this not tropically realizable? Maybe just because this one here is not tropically realizable, or is it really about the sum? That's something I would love to know. And so is it possible to realize just the Vamos matrix? I don't know the answer to that. And you guys like computations a lot, so there's this computational component to this workshop, and I think this is a question that we're in position to attack computationally. So let me spend 30 seconds saying what this would mean. What the question is, can you have an ideal, a tropical ideal, on 8 variables? so x1 up to x8, where the matrix in degree 1 on those variables, the polynomials that you put in degree 1, the subsets of lattice points, are the circuits of the Vamos matrix, or the unions of circuits. So for example, these four, they are like, yeah, this would be one of the circuits you put in degree 1, this is another one, and so on. But then you would have to think about the matrix in degree 2. So now it's a matrix on monomials of degree 2. And I think there are maybe 36 monomials of degree 2 in 8 variables. So this would be a matrix on a ground set of size 36. You know that it has to contain a lot of circuits. Like whenever you take a circuit in degree 1 and you multiply it by a variable, you should get a circuit in degree 2. So that already tells you that you should have a bunch of circuits in degree 2. But you need to kind of complete it to a matrix, because they are not a matrix yet, those collections of subsets. So can you complete it without, turns out this is equivalent, like having the right variety is equivalent to that matrix having rank 10, right? So the question is, can you construct this matrix in degree 2 of rank 10 having these pre-specified circuits coming from degree 1? I don't know the answer to that, but it cannot be that complicated. I don't know if it's closed under duals. It is closed under, like duality doesn't really behave well when taking ideals. But it is closed under minors. This is, you can realize that it's closed under minors. And actually my student Nick Anderson proved that there are infinitely many forbidden minors for this. So it's not clear what this class is. That's all we know. What I just said is all we know about this class. It contains all realizable matrices. It's not all matrices. It's closed under minors. It has infinitely many forbidden minors. And I think these days I'm leaning towards thinking that it might be just all realizable matrix. It might be that no matrix that is not realizable. Yeah, that is just the realizable matrix. For instance, this would be false, and we should be able to prove it maybe computationally that you cannot construct a matrix on rank 10 on these 36 monomials of degree 2. All right.
So one question. So the Vamos matroid is the smallest matroid that is not realizable if you fix the size, like according to size. But the non-pappus is the smallest if you like go, rank 3.
That's right, yeah.
Have you tried that as well, or?
No. I mean, that would be the matrix in degree 2 then would be, on the ground set would be all monomials on 9 variables of degree 2, which is much bigger. But maybe the rank would be not 10, but 6 or something. That could also be something that is maybe easier. Yeah. Maybe just because of time reasons, there's also some more recent work that we've done regarding the Nullstellensatz. Maybe I won't go so much into detail about this, but the classical Nullstellensatz for an ideal tells you that if the variety of your ideal is contained in some hypersurface, in the variety of a single polynomial, then some power of that polynomial lies in the ideal, right, over an algebraically closed field. And it turns out that something like that, we wondered if something like that was true tropically. Is it true that if you have one of these tropical ideals, one of these combinatorial ideals, and maybe the variety of that ideal is contained in the variety of one single subset, is it true that maybe after adding S with S, and this is like Minkowski sum of lattice points, enough times you get a subset that actually had to lie in your ideal? We cannot prove that as it is there. We can prove it with the saturation. So saturation just means take the sum of S with itself. And that's a complicated, there's a lot of arithmetic complexity there because you're adding lattice points, but if your lattice points are not they don't fill a whole polytope, then you might have holes, and controlling what holes appear is difficult. And there was a poster by Santiago about that. But if you just fill all the holes, like saturate, take the convex hole and take all lattice points that lie in there, then you get a subset that has to lie in there. Okay? We can prove that. Yeah, this specializes to particular instances, things that we have seen, for instance, in other talks, that if your variety is empty, then it has to contain a singleton, and that's a special case of what is there. Maybe not go into details. It implies things that are not trivial about classical ideals. So for instance, if you take a zero-dimensional ideal, a usual one with coefficients in a field, then it turns out that you can prove that it contains polynomials of arbitrary Newton polytope. For any polytope except for the point, you can show that some dilation of that polytope is the Newton polytope of some ideal in your, okay? And yeah, here I had something else about how this has to do with really arithmetic complexity. It tells you things like, okay, if your normal fan of a polytope refines the normal fan of another polytope, which is like saying that the variety of one subset is containing the variety of a principal ideal, or contains the variety of a principal ideal, then some dilation of that polytope has the other polytope as a summand, but actually stronger than that because it's not at the level of polytopes, but it's at the level of lattice points. It's telling you like every lattice point in the dilation of P, you can write as a lattice point here plus a lattice point here. So it really has to do with this integer decomposition property of polytopes, and that's very much what the complexity of these taking sums of S with itself has to do with. Yeah, also ask me later if you're interested in that. And let me just finish with a couple of questions that maybe I thought this community would like. One of them is how can we finally describe tropical ideals, right? So as I defined it over here, I'm telling you a tropical ideal is an infinite tower of matroids, and how can I email you a tropical ideal is not clear. How can I send you this infinite tower of matroids? And actually, with my student Nick Anderson, we computed just tropical ideals in one variable, and we realized that there's a lot of them. There's uncountably many. So there's no hope for them to be finitely determined, right? With finite information, even in one variable, you can only determine countably many of them. So yeah, that, as I said it over there, is not true, but it might be just like the real numbers, right? Like real numbers are not finitely determined, and still we mail real numbers to each other every day. So maybe there's some subclass of tropical ideals that can be finitely determined, and that's why I have some. So what are the algebraic tropical ideals, the ones that I can send you? I would love something like what you said, that if I tell you these 7 matrix degree 1, 2, 3, up to 7, and then I say there must be some way of saying, and from there on just continue canonically or something. I don't know what that means. I would love to make that precise. So that's one thing that I would love to know. Pick your favorite commutative algebra book, open a random page. What does that mean for tropical ideals? So one of the big questions, the big problems of this is that there is no notion of sum or intersection. They are not closed on, tropical ideals are not closed on their sum of intersection. So making some operation that behaves as if it was sum or intersection would be useful. And yeah, prime ideals I mentioned already that we don't know what they are. Primary decompositions would be even better, and it's very nice for algebraic geometry. Free resolutions, I think this is something that really should be. There's something to say here. How can we resolve one of these combinatorial ideals? And I think it's possible because we know how to do it for monomial ideals and even for binomial ideals, right? Like it's just about the combinatorics of the supports of the polynomials, not so much about the coefficients. So there should be some framework in which resolutions of these ideals encode like many of a framework where we can put many of the things we have said in this conference about free resolutions for monomial ideals or binomial ideals. And also, yeah, what can we say of the tropical ideal corresponding to a binomial ideal? Like that, there should be some, again, binomial ideals or lattice ideals, as we saw this morning. They're very combinatorial, and they really are about the support and the differences of the two binomials. That's all encoded by just looking at the supports of the polynomial. So is there something interesting to say about the class of binomial ideals, tropical ideals that are binomials? Are all of them realizable or not? Maybe yes. So yeah, let me stop there. Thank you very much.